let's start with the question. Again, what is the nature of the square root of 2? We talked about this last time. It's an irrational number, right? Can't write it as a ratio of integers. We also said it was algebraic as opposed to transcendental. It does solve a simple equation, a simple polynomial equation, x squared minus 2 equals 0. But how do you know it's irrational? To prove it, you assume the opposite. We want to prove that the square root of 2 is irrational. In other words, I could write that as an if-then statement. If x squared equals 2, and to keep it simple, x is positive, then x is irrational, meaning it's not rational. It's not an element of Q, the set of rational numbers. I said the proof is my favorite proof in all of creation, right? All of reality. I think it's the most beautiful proof that there is. So how can we say it's the most beautiful proof that there is and not actually do it, right? We need to do this proof. It needs to be a part of this course, even though it's a numerical analysis course and we don't talk a ton about proofs. I mean, we do some proofs. There's a fair amount of theory in here, not quite as much as real analysis, but we do want to be able to do some proofs in here. And this is one of them, since it's the most beautiful. We just have to do it. And yeah, it's an argument by contradiction. How else are you going to prove something is not rational, than to, well, say, what if it is rational? What would that lead to? What kind of conclusion could you make? It must be somehow a contradictory assumption. So that's what you do. Assume to the contrary that x is rational. X is an element of the set of rational numbers. And just play with that assumption and see what kinds of conclusions you can make with it. Maybe you can't make any kind of conclusions that contradict each other, but maybe you can. You gotta play with it and see what happens. So what would that mean? What would it mean for x to be an element of the rationals? It would mean, as we talked about last week, that x could be written as a ratio, a over b, where a and b are integers, elements of z. Z stands for the set of integers. It's shorthand for Zahlen, which is a German word for number. -3, -2, -1, 0, 1, 2, 3, etc. Whole numbers, positive or negative, including 0. Although we don't want to divide by 0, so we should say b is not 0. And think back to when you first start learning about fractions. Fourth grade? Fourth grade, when you first start learning about fractions, you learn about, well, what do they represent? Like pieces of pie or something, pieces of a whole. You maybe learned how to add them and multiply them, fourth or fifth grade. And you also learned to make them simpler in a certain way. What's that called? When you got a fraction like 20/15ths, what does it simplify to? 4/3, right? You can reduce the fraction. You can always reduce your fraction, right? So we can certainly assume, without loss of generality, that we have reduced this fraction. WLOG is the common mathematical shorthand for without loss of generality. A over B is completely reduced. You have reduced that fraction to lowest terms, you might say, which, and here's the relevant part about that, in particular means either A or B has got to be odd, one of those two, maybe even both of them. They can't both be even, because if they were both even, you could reduce it further, right? 6 divided by 8 can be reduced to 3/4. You could always factor out a 2 and cancel the 2's. So at least one of those has to be odd. And either A or B, or both, that's an inclusive or, is odd. Now, you wouldn't necessarily know in this proof that you'd need to make that assumption, but it certainly is an assumption that can be made, and it turns out to be the key to the proof, besides assuming X is rational to begin with. To go ahead and assume you reduced it so that either A or B is odd, and possibly both of them are odd. They can't both be even. Then you just got to play with this. What am I assuming about X? You got to use that fact, right? This assumption that X squared equals 2, that must be relevant somehow, right? When you're doing a proof, you got to use what you're assuming. So let's use that. Since X squared equals 2, that means, well, square that fraction. A squared over B squared equals 2, right? You square fractions by squaring the top and squaring the bottom. So A squared equals 2 times B squared. Just multiply both sides by B squared. So what? Stare at that for a while. Maybe go get some coffee. Stare at it some more. Maybe go take a nap. Stare at it some more. And then all of a sudden you realize, hey, you know what? That's telling me actually something kind of significant. It's telling me A squared must be even because it's 2 times some integer. I guess A must be the even number. That seems a little weird. Therefore, A squared is even. And therefore, 3 dots is nice shorthand for therefore, A is even, right? Because if you square an odd number, you'd get an odd number. Isn't that wild? By assuming X squared equals 2 and A over B is completely reduced, we can conclude that the numerator must be the even number. That's kind of wild, unexpected. All right, well, are we done? Well, we haven't really reached a contradiction yet. Maybe we should continue exploring. Say A equals 2 times, I don't know, how about C? For some integer C. That's what it means to be even. What would happen if I substitute this into that equation in place of A? Therefore, 2C squared equals 2B squared. But 2C quantity squared is 4C squared. Okay, I'm going to do shorthands with my sentences. Now I'm just going to do implications. That implies B squared is 2C squared. Therefore, B squared is even. Therefore, B is even, right? Again, because if you square an odd number, you'd get an odd number. Wait a minute. You can conclude B is even as well. But wait a minute. We assumed A over B was completely reduced, so one of those two had to be odd, and we concluded that they're both even. What in the world's going on here? Alarm bells should be going off. What have we done? Does this disprove the validity of math? No, what it is it's a logical contradiction. And what that means is your original assumption must have been wrong. We have concluded, well, we certainly can reduce the fraction. And based on this assumption that X squared equals 2, we conclude that both A and B are even, so the fraction actually wasn't reduced. That's a contradiction. Can't happen. Sometimes you'll see little star symbols like this, but they're actually not star symbols. Whenever I saw a math professor draw that, I thought it was a star. It's actually 2 arrows pointing at each other. Sometimes they draw it more like this, and so it looks a bit more like a star. But there's actually 2 arrows pointing at each other. Logical contradiction. Therefore, our original assumption must have been wrong. Is wrong. Our original assumption was that X is rational. Therefore, X is not rational. QED, or praise the Lord, we are done. We have proved that if X squared equals 2, then x is not rational. Now, actually, I didn't need that extra assumption that x was positive there. This would be true even if x were negative, but I was thinking of positive square root of 2. That's what the symbol means, is the positive square root of 2. Great. Square root of 2 is not rational. Isn't that beautiful? I think this is the most beautiful proof in the universe. I do. Second place is the proof that there are infinitely many primes. I don't like that one quite as much. You can actually write that one maybe a little shorter, but I think this one's a little bit more fun. Personal preference, I guess. So it's an irrational number. You can't write it as a ratio of whole numbers. You also, the decimal expansion must go on forever and ever without a repeating pattern. What is the decimal expansion? Well, here's 1,000 digits of it. One 1.4142135 blah 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 blah. Wait, okay, that's 1,000 digits of that. That's 10,000 digits. There's 10,000 digits. Wait a minute. How's this figured out? Has anybody ever squared this number and shown you gotten 2? It goes on forever and ever without a repeating pattern. How do you even know there is such a number? Is it well defined? In our proof, we actually did not prove that such a number exists. We just proved that if it does exist, it's not rational. Whoa. We didn't really prove it exists. But wait a minute, you've learned about square roots since 6th grade? I don't know. You've thought about things like square root of 2 since 6th, 7th grade. Were we lying to you? Does the square root of 2 really exist? Yes, it does, and we can prove it. How? Well, the simplest way is with the intermediate value theorem. Theorem, square root of 2 exists. In other words, i.e., there exists a number, a real number, such that x squared equals 2. Proof does use the intermediate value theorem, like we talked about last week. Let f of x equal, okay, write down your polynomial. That's a simple polynomial whose roots we know are plus or minus square root of 2. By definition, effectively. Note that f, being a polynomial, is continuous on all of R, and in particular, it's continuous on an enclosed interval. Also note, square root of 2 is about 1.4. Okay, f of 1 is 1 squared minus 2 is negative 1 is negative, and f of 2 is 2 squared minus 2 is 4 minus 2 is positive. Let capital K equal 0. Remember this from last week? Which is between f of 1 and f of 2. Because f of 1's negative and f of 1's positive. K is 0. What's going on here graphically? Well, the part of the graph we care about looks like this. Here's 1, here's 2. The graph is crossing the axis. The intermediate value theorem says there's some value of c that's a root of this polynomial. The IVT implies there exists a C. You can even say it's in the open interval from 1 to 2, such that f of C is 0, i.e., what's K? I.e., C squared minus 2 is 0, i.e., C squared equals 2. So C is by definition the square root of 2. I'll do one more i.e. C is square root of 2. I.e., by the way, is a Latin abbreviation, if you've never known this. I forget what it stands for, but it means in other words. Praise the Lord. Does this feel like cheating, though, in any way? Doesn't it feel too easy? Like, proving square root of 2 exists should be harder than that, shouldn't it? I mean, after all, it's this infinite repeating decimal. Well, non-repeating decimal, I mean. Nobody knows all the digits except God. Is this really good enough? What key complications do you think this is hiding, so to speak? It's proof that it just seems too easy. What subtleties is it hiding? It must be hiding some sort of subtleties. Somebody who's had real analysis. Anybody? I think a few of you have. Didn't you last fall? What do you talk about the first few weeks in real analysis? Preview for those of you who have not had it. Completeness. Completeness axiom, soups and infs. Least upper bounds, greatest lower bounds. If you have no idea what I'm talking about, it's okay. You have it to look forward to next fall. Kind of hard stuff, though. This is hiding that. It's essentially hiding it in the phrase continuous on R. Because what does it mean for a function to really be continuous on the real numbers? And what are real numbers to begin with? Well, you say they're rationals and irrationals. Yes, but that's kind of assuming decimal expansions really exist and describe numbers. I mean, I know you've always been taught that, but that's kind of an assumption that needs some justification as well. Will we justify that in this class? We'll talk about continuity a little bit, probably not today, more rigorously, but not right now. Yeah. The hard work is in describing what continuity on the real number system means and what real numbers even are without talking about decimals. I mean, you can certainly talk about rational numbers without talking about decimals. But how do you talk about real numbers, including irrationals, without talking about decimals and without... Yeah, it sounds hard, and it is hard.